Now that we've done the discovery and we've gone over our vocabulary, we can come up with some connections. As I write these connections down and as you're copying them down, you're going to hopefully, they'll see them a little familiar from part C. Okay. It's important to know that there are an awful lot of questions on the exam which will be based off of these connections that you see here. So as we get them down on paper, you want to go over them, maybe make some flashcards, because it's very important for you to learn these connections and have them ready to go at a moment's notice. So if we go back to, and we kind of compare what we saw in part C, as well as what we saw with this graph right here. Okay. And now that we know our vocabulary, we can come up with the following connections. Okay. A function is increasing when the derivative of the function is positive. Okay. Remember, the derivative is the slope of the tangent to the curve. So we drew a whole bunch of slopes on our graph. And it turns out that those slopes were positive when our function was increasing. So that means the derivative is positive when the function is increasing, and the function is increasing when the derivative is positive. It goes both ways. And conversely, when function is decreasing, the derivative is negative. Right? So a decreasing function means a negative derivative, and a negative derivative means a decreasing function. Again, it goes both ways. Critical point, we already talked about in the previous video. Critical point occurs when f prime, when the derivative equals 0 or does not exist. The relative max, that was the top of the hill. So one of the connections, which you hopefully wrote down from those graphs, is that the relative max occurred when the derivative changed from positive to negative. So f has a relative max when f prime changes from positive, and I'm going to write positive as a plus sign with the circle around it, from positive to negative. That's when you get a top of a hill, when the derivative changes from positive to negative. You get the bottom of the valley, which is now going to be known as a relative min. That occurred when the derivative was negative and then switched over to positive. Concave up, that's our curvature. This is U-shaped. All right. So when we go back here, get the graph up here again. Okay. What was going on when we were U-shaped? Well, when we were U-shaped, the slopes went from -9 all the way up to 3. And then the slopes also went from -1.5 all the way up to 6. So the slopes were increasing when we were U-shaped, or concave up, and the slopes were decreasing from 3 all the way down to -1.5. The function is concave down. Right, so going back here, concave up, the slopes were increasing, but the derivative is the slope. So that means that the derivative is increasing. All right, so f is concave up. F is shaped like a U when its derivative is increasing, and an increasing derivative means a concave up function. Vice versa, a function is concave down, or shaped like an upside down U, when the derivative of the function is decreasing. And again, this goes both ways. Decreasing derivative means the function is concave down function means its derivative is decreasing. The point of inflection, that occurred when our function's derivative, the slopes, changed from increasing to decreasing, or vice versa. So f prime changes from increasing to decreasing, or decreasing to increasing. In other words, where the derivative has a relative extreme. Now, we also want to look at connections between a function and its second derivative. Okay, well, how can we do that? When is a function concave up? Well, a function is concave up when the derivative is increasing. But watch what I'm going to do up at the very top. I know that a function is increasing when the derivative is positive. Well, if I put a little marker here, now I have f prime is increasing. If I put a marker on this side, I need to put a marker on that side. So when f prime is increasing, the second derivative is positive. And when f prime is increasing, the function is concave up. So by the transitive property, a function is concave up when f double prime is positive. A function is concave down when f double prime is negative. A function has a possible point of inflection, we already talked about this, when f double prime equals 0 or does not exist. And a function has a point of inflection when f double prime changes sign. Doesn't matter if it's positive to negative or negative to positive. When the second derivative changes sign, the function has a point of inflection. So these connections right here and up here are extremely important and need you to learn them, become familiar with them, because we're going to use them in all of the examples that follow suit.